let's make a start. So good morning, everyone. My name is Tuan. I'm a professor at the University of Melbourne. I'm going to chair the session, this morning session. We have 4 presentations this morning, and this session is about non-destructive techniques for structural health monitoring. So we have the first presentation would be presented by myself. We also have really excellent presentation coming from RMIT, from also CSIRO and University of New South Wales. So again, really want to thank all the participants. We had a great yesterday with so many wonderful presentation, and we learned a lot. So this morning we are continuing with some new techniques, and people have been using structural health monitoring techniques, especially the non-destructive techniques. So we really want to share our experience and present, and hopefully to hear the feedback from colleagues and friends. Really want to hear many experts from industry who are joining today. So with that, I think I will start my presentation, the first presentation for this session. So this is the presentation about vision-based automated crack detection using CNN. People know very well about the convolutional neural network for condition assessment of infrastructure. So this is not a new topic because many people have used these techniques, but we are assessing different models to see which model will give us the best accuracy and running time. So this joint work between our group, we have a couple of people involved in this project. So to start with, just want to give a bit of background, and then we are going to talk about the approach, the data and implementation in this particular project, and also to report the result we achieved from this work. So as you know, we are facing a big problem. Infrastructure in Australia and around the world are aging. We have a lot of big tasks to inspect, bridge maintenance, and how we actually can manage that process, because it's very time consuming and costly. In Victoria, there's about 7,000 bridges will require regular inspection. In New South Wales, over 40% of the bridges are over 40 years and will require regular monitoring. And globally, we say the budget for bridge inspection is forecasted to be rising 4 times by 2030. So really a lot of work needs to be done in this area. So we know the bridge in general, we have different methods. There's the mainstream method. In Victoria, for example, level 1 and level 2 inspection will rely on visual inspection. So we need to have a qualified person, inspector, to detect any damage. It can be cracks on the surface of a bridge. So those manual inspection practice always really depend on people expertise and exerience, and it's very costly, time consuming. And in many bridges, the condition can be very sometimes dangerous to have access to the bridge. So really we need to think about how the whole process can be done in more automated ways. So we know recently with the advancement in automation technology, AI, machine learning, also drone technology allow us to really assess and have a visual inspection from remotely. So it can be done autonomously using some intelligent inspection system. And of course, we have to rely on some camera attached to drone, and then we can take high resolution images. And that also requires some automation detection. We see there's some crack, how we actually can detect that in real time or near real time. The advantages are very clear. So that allows actually low cost solution to detect and report the damage, potential damage. So we did a review in these areas to look at what are the method for vision-based automated condition assessment. So broadly, we have 4 different assessment models here. So basically, the first one is about image processing method. The second one is the region-based classification method. The object detection method applied to crack detection. The fourth one is semantic segmentation method. So this work is part of the work internally funded at our university, and we published a paper in the Journal of Structural Health Monitoring recently. It's the vision-based automated crack. So in this paper, we listed all different methods, and we look at the advantages and disadvantages of different methods. So of course, CNN is one of the most popular method here, but we are also looking at some other method as well. So let's look at a bit more detail about those different approaches. So we use the patch-based approach with 15 different deep learning classification models. So the method is quite straightforward here. You can see with an input image, we actually divide the image into a matrix of 4 by 4. So there's a 16 patches. So this is the method, and then we can each patch can be fed into a CNN model, and the image can be resized and basically using the CNN model to detect crack if the image here contain any crack or no crack. So let's look at that a bit more detail. So you can see in this slide the 3 main steps. So an input image is divided into 16 patches. And then we use the deep learning to train the model. And then the third step is to test this method to see how this method can detect different type input image and see how accurate the method can provide the accurate prediction. So there's many different models, but in this work we summarize here 15 deep learning models in this table, going from the top, quite popular, the AlexNet. So you can see the input size and the number of parameters. So each model contains million parameters, as you can see. For example, the AlexNet has about 57 million parameters here. And other methods, for example, the VGG, the Vision Geometry group here, 16 or 19, contain about 130, more than 130,000 million parameters. So each model, of course, have different advantages and disadvantages, and we have summarized that in our paper. So let's look at the data, because as you know, in deep learning algorithm, the data is very important. The quality of the data, the amount of data is really important for the accuracy of the method. So we have in total about 2,000 images to train the model. We also have about 129 validation images and about 300 classification testing images. So we look at, you can see the number of cracks and non-crack. The data imbalance is also important because out of those many images, 73% of those images, there's no crack. And we also only have about 27% have some cracks in there. So we use some method we call it a weight tensor approach to look at how we can weight between crack and non-crack images. And the implementation of the data here, because we really need to train the model and to basically use some performance matrix to evaluate the performance of the model. So how we do that? In this case, we use the matrix is called confusion matrix, and it actually can provide information about if the model is true positive or false positive. So there are different classification here. So true means the image is actually correct, and then it can be true positive. That means basically the detection show that it's actually the crack in the image, and the method allows the prediction is also positive. So I think there's 4 different options here, and we use those outcome to look at the accuracy and the precision of each method. So with that, I'm going to look to show you here how we implemented those different models. The models were implemented using popular the PyTorch library, and we used the NVIDIA GPU, which is a cloud-based service using a GPU card. And because of the advantage of the processing time, I think it provides really good platform to test those models. So in this particular case, is the comparison between the train accuracy and the valuation accuracy. So we can see the improvement after training, it improved the accuracy a lot. So the result here, you can see in these slides, it actually presents just one case, which is the VGG16 model, deep learning model. And you can look at the image from left to right. So it actually, the top one is really about the predicted output. Sorry, the actual manually annotated actually images, and the bottom one here is actually the predicted output from the VGG16 model. So we can see the difference between different images. You can see the surface texture, the background, and also the brightness are quite different. But the model predicted quite well. You can compare, let's say, A and I at the bottom here. I think it predicted quite well. And we look at different background and the surfaces. It also predicted quite well. So I think at least in this case, you can see the model correctly predicted all 16 batches containing cracks. So let's summarize the result of the models we investigated. So you can see in this table, the accuracy is actually quite consistently, and of course this is extremely good. But of course there's some differences, like the VGG19 show the highest precision. Of course, it also achieved the highest accuracy. So in general, all the 15 models, deep learning models we investigated perform pretty well. The accuracy in the range of between about 0.94 to 0.96, and precision is also quite good. So we are really happy with those models. And compared to some of the previous study in literature, I think we see a good improvement here. And also we compare the efficacy of those 15 models using another different techniques. So again, it show really good result, and of course it can be applied in other cases. So another important factor is the inference time. So how quickly can we predict and assess those images? So in this case, we also found that, for example, the VGG acquire about 220 milliseconds to assess. So those time fraction is important, because if we have to assess 1,000 images and it requires some real-time type assessment, it actually show you it might take a couple of minutes to assess a certain location. So we did that in actually real time, and we show we can reach almost a near real time detection in this using those methods. So again, there's still a lot of work can be done to further improve the running time. But at this moment, I think we are happy to say, I think it reached really good running time for us. So in conclusion, the automated crack detection model important to assess those aging infrastructure. And in this study, we use the patch-based automated crack. We train different models containing many different patches, and we achieve a good result of the 15 deep learning models here. So hopefully in the future, the running time can be further improved. And of course, if we have more data to validate the models, I think that would also improve the accuracy even further. So with that, I just want to stop my presentation here, and hope if you have any comments or questions, we'll be happy to answer. Thank you. So is any question?
Any question, you can turn on your mic and then you can ask directly.
Good morning. Thanks. This is Ali. Ali Yassi. I'm just listening to your presentation, and thanks. It was very interesting. I'm wondering, have you ever used the LSTM network to train the CNN instead of using the picture, like the short-term memories as a signal processing?
Yeah, actually, it's a very good question. Thank you for asking. I think in this case, we only look at that data set for the crack data set. And again, the paper we published recently showcased these techniques. So 15 models, deep learning models, we investigated in this case. Yeah, we are thinking this method can be applied to other contexts, but at the moment we just use the data we have, and looking for opportunity to have some even more data to validate those models.
Hello, Professor Tuan. Can I ask a question?
Yes,
yes. I'm just wondering, because you tested different classifier. So what is the size of the data set, and where did you get these real live photos from?
Yeah, so I think it's a combination of some of the crack database we got from literature, but also we did some probably about, I think, a third of that database is from our actual collection. Of course, we have to make sure that we have different texture the brightness and also even background and lighting conditions. So that really, of course, doesn't cover everything, but we try our best to capture those different conditions.
Okay, so does that mean that your team went to the real bridges and took some photos?
Actually, yeah, some of the work we did, of course, the non-crack one, we got a lot of photos, but too tricky to look at some crack images. It's not coming. The crack image is mainly coming from some of the library we have access to, but we took also a lot of photos for non-crack photos.
Thank you.
Hello, Professor. Hi, Professor Tuan. This is Ali from University of Sydney. That was very interesting presentation. Actually, I read your paper. It's really nice paper. My question is, I presented a similar thing yesterday, and what we realized the issue was the combination of crack and non-crack and other elements, like, for example, corrosion or any other surface similar to crack, but they are basically not crack. And I was wondering if you considered those in your data set.
Yes, actually, we really, the time required for the team to actually alternate all those different photos, so non-crack and cracks. So it took probably about, I think, few months for I got some research assistant to have to alternate all those 100 images like that. So hope we can share that database with everyone if you are interested.
Yeah, definitely. Yeah, that would be great. Actually, we collected roughly around 200,000 images.
Yeah.
And that is very comprehensive. So we'll be happy to share that and collaborate in that area. That would be great.
Excellent. Thank you, Ali. I'm really looking forward to that.
Yeah, definitely. Yeah. Thanks.
That'd be wonderful for the community, guys, if you could. I have a general question maybe for Tuan and Ali. My question really around deep learning and machine learning black boxes is the lack of explanatory variables or the lack of explanation as to why the algorithm thinks a crack is a crack or why it thinks it's not a crack, because that's how we then can learn from what it's thinking, and vice versa. We can also correct it into thinking what we know to be true. And I know in medicine, we've probably seen about the success of AI in terms of recognizing skin cancer, but the work there is now around trying to turn that into explanatory, to explain to the doctor why it thinks it's skin cancer or why it thinks it's not skin cancer. Is that kind of explanatory aspect of AI ML something that we're able to look at rather than just treating them as a black box?
I think this really excellent question, Colin. One of the team members in this project is actually the main work coming from medical. He uses these techniques in medical context, looking at X-ray images. So I think we learn a lot from what have been done in medical using deep learning. So I think this is still a learning ongoing for us to explore the method. But again, the deep learning is probably not black box at the moment. I think we learn a lot from this project to look at different models, and hopefully it can be shared, and I think we can make it more transparent for people to learn and pick up that. The question is how we can assess them in different contexts, from medical to civil engineering. Of course, it's a lot of common features, but a lot of differences as well. I think we had really good discussion here, but I think conscious about time, so I have to really move on to introduce